Hello and welcome back to The Explainer. Today we're diving into the alkali metals, from mystery to mastery. We are going to be investigating some of the most dramatic, incredibly unstable, and frankly, absolutely fascinating elements on Earth. Let's just jump right in. Okay, let's dive right into this with a question. What kind of metal explodes in water and cuts like butter? It sounds like a total riddle, right? Well, by the end of this explainer, you're going to understand not just what these bizarre elements do, but the invisible microscopic secrets that actually drive their spectacular behavior. See, when we think of metals, we usually picture steel girders, heavy iron anvils, or solid gold coins, things that are hard, heavy, and super durable. But there's a specific family of metals that totally shatters those expectations. They are incredibly soft, highly volatile, and dangerously reactive. I am, of course, talking about Group 1, the alkali metals. These guys are the absolute stars of our show today. Now, what makes this specific cast of characters so compelling is their sheer instability. Because they react so incredibly fast with other elements, they are absolutely never found uncombined in nature. No way. You will never just walk outside and trip over a pure chunk of one of these metals. They are always bonded away, hiding inside other compounds, just waiting for a clever chemist to isolate them. To really understand why, let's take a macro look at the periodic table. Group 1A sits proudly right there on the far left edge. And honestly, this specific location dictates their entire personality. They're basically the eager joiners of the elemental world. They will happily bond with virtually any other element they come across, with the sole exception of the noble gases all the way on the far right, which they just can't react with. Let's meet the team real quick. We've got lithium, the lightest metal, sodium and potassium, which probably sound pretty familiar. Then we move down into the heavier hitters, rubidium, caesium, which is extremely heavy, poisonous, and reactive. And finally, francium, which is so rare, radioactive, and dangerous that very little is actually even known about it. But what's truly amazing is the everyday connection here. Despite being wildly unstable in their pure forms, sodium makes up half of common table salt. Potassium is famously found in the bananas we eat, and rubidium, that is the secret ingredient that gives fireworks their brilliant red color. So they're incredibly dangerous, yet intimately connected to our daily lives. So the crucial takeaway here is that their physical properties are just bizarre. They have a really low density, low melting and boiling temperatures, and they are extremely soft. You can literally slice right through pure lithium or sodium with a dull butter knife. And when you make that fresh cut, the inside is bright, silver, and shiny, a very typical metallic look. But here is the paradox. Almost immediately, right before your eyes, that shiny surface tarnishes and turns completely black as it reacts with the oxygen in the air. The pure metal essentially dies the very moment it touches the atmosphere. And that rapid energy release beautifully illustrates another one of their stunning properties. When you introduce these pure metals to a flame, they release energy in these breathtaking ways. Chemists call this a flame test. Just look at these distinct, brilliant colors. We have the gorgeous crimson red of lithium, the bright, vibrant yellow of sodium, the lilac of potassium, all the way down to the blue-violet of caesium. It's a gorgeous visual signature for elements that are otherwise incredibly difficult to keep pure. Okay, so we've seen the macro-level drama, right? They turn black in the air, they burn in brilliant colors, they're soft enough to cut like cheese. But the real question we need to answer is why? Why are these metals so uniquely chaotic and reactive compared to literally everything else on the periodic table? Well, to answer that, we have to transition from the visible stuff we can see down to the invisible atomic engine driving it all. The answer lies entirely in their electrons, specifically their valence electron. Every single alkali metal has an electron configuration that ends in ns1. Now, what does that mean? It means they have exactly one incredibly lonely electron sitting way out in their outermost shell. If we were to sort of anthropomorphize these atoms, we'd say they have a destiny. They desperately, desperately want to lose this single electron. Shedding it allows them to achieve a super stable noble gas-like configuration with a positive 1 charge. They will vigorously react with oxidizing agents just to kick this one piece of baggage to the curb. Let's move along and see how this builds into a very specific set of rules for reactivity. As we move down Group 1 from lithium at the top to caesium at the bottom, the atomic radius increases. Basically, the atoms physically get larger because they're packing on more electron shells. As a result, those inner electron shells act like a thick shield, blocking the attractive pull of the positively charged nucleus in the center. Because that outermost lonely electron is now further away and heavily shielded, the ionization energy, which is the energy required to pull that electron away, drops significantly. What is really visually striking about this trend is this steep descending staircase of that first ionization energy. Just look at that massive drop. It represents exactly how much easier it becomes to strip away an electron as you go down the list. Lithium, being the smallest atom at the top, holds on to its electron the tightest. But look down at Caesium. Because it is so physically massive, it barely has a grip on its outer electron at all, requiring vastly less energy to just rip it away. So this summarizes the whole story beautifully. As the atomic radius gets larger, the ionization energy gets lower. And because that outer electron is so much easier to lose, the reactivity skyrockets. Lithium is the least reactive of the group, sodium is more reactive, potassium even more so. By the time we hit cesium, the loss of that electron is so completely effortless that the resulting reactions are incredibly violent. In fact, due to the weirdness of relativity, scientists actually predict cesium is even more reactive than francium. And speaking of violent reactions, let's examine their most famous party trick, reacting with water. This is the general equation for any alkali metal reacting with water. Two atoms of the solid metal react with two molecules of liquid water. And what happens? Well, they violently rip the water apart to form an aqueous metal hydroxide. That's a highly corrosive strong base, like sodium hydroxide or caustic soda. But look closely at the end of the equation, H2 gas. They release pure, unadulterated hydrogen gas. And this specific combination is exactly why these elements demand immense respect in a laboratory. We are dealing with a serious dual threat here. First, the reactions release hydrogen, which is an extremely flammable gas that can actually ignite spontaneously just from the intense heat of the reaction itself. That's what causes those famous science class explosions. Secondly, the hydroxides they produce are highly corrosive and can cause severe skin burns and permanent eye damage. Because they are so volatile, we absolutely have to rely on strict safety protocols, like these provided by the CLEEPS safety sheets. You cannot just leave these metals sitting out on a desk. They must be stored completely submerged in liquid paraffin, which you might know is mineral oil. This physically blocks the oxygen and moisture in the air that they desperately want to react with. If you take them out, you never, ever use your bare hands. You handle them using forceps while wearing eye protection behind a safety screen. And if they happen to ignite, you cannot use water. Obviously, you must have a container of dry sand available to smother the flames. I think this quote from the safety manual really puts the whole thing into perspective. Conduct all investigations on a small scale, generally use a rice grain-sized piece. Just imagine that for a second. A piece of pure sodium or potassium the size of a single grain of rice contains enough reactive energy to dramatically demonstrate its power. Anything larger than that little grain, and you seriously risk exploding your apparatus and showering the entire room in molten, corrosive metal. Now, if you thought that was intense, listen to this hidden danger that's specific to potassium. Over a period of years, even while properly stored under oil, a sample of potassium metal can develop this custard yellow coating. This isn't just normal tarnish, it is potassium superoxide. And according to the safety sheets, this yellow crust is so phenomenally unstable that just the slight downward pressure from a knife blade trying to cut it can cause the entire sample to detonate right there on the table. It's a brilliant juxtaposition, isn't it? On one side, we have the natural chaotic state of the alkali metals. They're wildly unstable, rapidly tarnishing blacks, spontaneously igniting and exploding the second they touch water. But on the other side, we have the controlled mastery of science. By truly understanding their atomic properties, we can safely submerge them in oil, handle them with precision, and unlock their beautiful, controlled flames for study. Which brings us to a final, pretty provocative thought to leave you with. We've seen these metals burst into flame, we've gone over the terrifying hazard warnings, and we've learned the strict safety rules. But remember, all of this macroscopic chaos, the fire, the explosions, the rapid corrosion, is driven entirely by the overwhelming desire of an atom to lose just one single microscopic electron. So how much explosive power is really waiting inside the things we cannot even see? Thank you so much for joining me on this explainer. Keep wondering, keep learning, and I'll catch you next time.